All right, good afternoon, class. Hopefully, we're all doing well today. So, the homework one will be due tomorrow at midnight, and there's no 24-hour sort of grace period. I guess for written assignments, it sort of makes sense to not really, have that because it shouldn't be as stressful like doing your programming assignments, where maybe having more time to figure it out for a written assignment, I would imagine that would be less stressful to get it all done. But make sure you get into a PDF form. It's either using some type of a writing app or on a tablet, or scan the your written portion into a PDF file and have it just be one file with all the pages on there, so it's easier for the grader to sort of go through all of that. Um, I do have an assignment 2 up as well, so I guess I'll talk about that first. Then I'll sort of finish up the last of the master theorem problems, and then we'll go on to other topics. So let's go ahead and start the screen share and begin. Okay, so kind of a flash warning. Here's a sort of a white background is about to pop up from the PDF. Just a little warning. Okay. So there's not much to say about this assignment other than just work out these recurrence relations. So I'll zoom in a little bit so we can see it a little better. It is posted on Canvas. I just posted it up recently. So I had this PDF already done, but I forgot to upload it last night. So I uploaded it right before class today. So just work these recurrences out using our standard, methods. So we had the expansion method, that tree method. We also had that antiderivative method on some of these, and also that one really weird, substitution one for the square root one. So the last one right here is where you want to actually use that. The rest of these, though, you can use expansion and recursive trees to solve them. So I said right there, express them in terms of omega, O, and theta. So the reason why is because if you notice on these problems, we have less than equal to, greater than equal to, and so forth. So for question one, it would be actually big O of something. Question two would be omega, because T of n is equal to or larger, so this is actually a lower bound of T of n. So this would be big O because T of n is less than this expression. This one would be omega because T of n is equal to or larger than this expression. And for equals, it would be just theta because it's exactly that. So that's really, I just did this just to like make it a little bit more, I don't know, creative for the assignment. But that's all there is to that. So, and actually I forgot the base cases. So all of them, T of 1 equals 1. Just like we've been doing for all of our recurrences so far. So just assume that T of 1 equals 1. So a size 1 input will take constant amount of time to process. So now for the ones that do follow the master theorem, additionally to working out and showing your work and using the expansion method or tree method to work out the recurrence and to get the actual figure out what's the growth rate of this recurrence relation. Also, on top of that, also show me the results using the master theorem. So go ahead and show me A, B, and C, in which case is going to be triggered on that recurrence relation. So for questions, I believe 2 and 3, you can actually apply the master theorem on them. Question 1 is not in the master theorem form. There is another sort of method of working this. I forgot the actual name of this person, but there's an actual method that you can use like a master type theorem for this type of expression, but it's a little bit complicated to do that. But I can maybe link a PDF or link a sort of a web page that goes over. I hear let me go ahead and just sort of, I guess it's muted now. So if you have a question, you can of course speak up. But anyway, so um, yeah, so these ones you can do a master type theorem, but it's a different sort of. I forgot the name of that person. But I can look it up and I can give that to you. But you don't have to do it for these ones. But for question 2 and 3, for sure you want to additionally, after you solve it using the recurrence tree or the expansion, also give me the results of the master theorem as well. So you can kind of practice doing that as well. But for most of these, though, I guess the master theorem is not too helpful, only for 2 and 3. But it'll give you a chance to practice that as well. So anyway, that's pretty much assignment number 2. So just work these questions out, and it's due next Friday. So that's about it. So any questions on this assignment at the moment? All right, so I'm guessing we're okay there. So let's go ahead and just now talk about the, let's continue on the last few sort of problems with the master theorem. So I'll do a couple extra ones. So let's look at this example. It's only a few more I'm going to do, then we'll go over kind of actual algorithms. So this is kind of like the equivalent in CS302. We start off with a bunch of math and big O notation and solving code snippets. This is kind of like doing that, and then we're going to actually go into actual algorithms. So let's go ahead and just finish up these last few examples. So in this recurrence relation, we'll have T of n equals 3 T of n over 2 plus theta n, and then T of 1 equals 1. So for this example, well, let's go ahead and sort of quantify all these. So A will be 3, B will be 2, and then f of n is just n to the first power, and C is going to be log 2 of 3, which will be roughly, I guess I can keep this here just as a little reference, it's about 1.58496, somewhere around that it's going to be. Okay, so now we want to go ahead and see which case of the master theorem we can apply this on. So I'm going to go to my notes for master theorem, since I can't memorize the master theorem. I just refer back to my notes on this. So the first thing is we want to, just like in Rick and Morty, start from indicators 2. So case 2, I want to start with that one because that's the simplest one to match with or eliminate. So case 2 would say if f of n equals theta of n to the power c. Well, f of n is n, and theta to the power c is theta of 1.584, so f of n is not theta of n to the power c. So I guess case 2 is already gone. So it has to be case 1 or case 3 in this situation. So case 1, let me go ahead, let's test out case 1. So for case 1, the following has to be true. So n has to be O of n to the power c minus epsilon. So if epsilon is like 0.1, some small constant, then n equaling O up to the power 1.4 or so, yeah, that would actually work. So it looks like to me, let me just go back to my notes, make sure I don't mess this up. It would be a case 1 scenario, so I was correct. This is going to be case 1. So again, we have a case 1 situation because this is definitely going to be correct. So if we pick some epsilon larger than 0, so I'll pick 0.1, this statement would be true. So definitely case 1 is going to occur. So then in that case, we have case 1. So case 1's result is going to be, it would be just n to the power, so T of n would equal theta of n to the power c. So it would be theta of n to the power, I guess, log 2 of 3, or you could also express it as theta of n to the 1.58496. But a more preferred result would really be just use theta to the power of n to the power log 2 of 3 would be the better answer, although both would be valid, but this is more accurate results. So we have a case 1 situation here as well. So let's go ahead and so in this case we can just set epsilon. We can just make it just, let's say 0.1 I'll pick, and then it's going to work because we can definitely see that n would be O of n to the power 1.48496 would be correct. So epsilon can be anything larger than 0. It can be any value, but typically it'll be some decimal less than 1, larger than 0. You can pick any value you want. I'll just pick 0.1, and we can definitely see this statement would be valid. So therefore case 1 occurs for this master theorem. So let's do another one. So how many more do I have left here? I think I have a few more, actually. So that's okay. More practice on this is actually a good thing. Let's go ahead and keep practicing. So t of n equals 2t n over 4 plus theta root n. And I guess, okay, I'll put t of 1 equals 1. This is kind of almost implied, but I'll put this there anyway, just to be consistent. So t of 1 equals 1, no brainer there. Alrighty, so let's go ahead and just sort of work this one out. So let's first get our constants. So a is going to be 2, b is going to be 4. I mean, I guess can't think of when it wouldn't, but really t of 1 would be some constant. So if you have a very constant small input size, it would be 1. So I can't really think of when that would be the case, because typically you got to have a base case for a recurrence function. So when you have some base case, you don't have to keep on recursively doing any work. So I guess there must be a base case at some point for recurrence. So that's your base case, essentially. So I guess there never will be a case where t of 1 wouldn't equal 1, because you gotta get a base case where it will stop recursively keep on calling this function. So yeah. So a equals 2, b equals 4, and f of n equals n to the 1/2. So then c, well, c would just be log 4 of 2, which actually would be 1/2 in this situation. So let's go ahead and first, as with the vindicators, let's start with vindicators part 2, and let's see if we can match it to case 2, because that's the simplest one to match with and simplest one to eliminate as well. So case 2. So is this correct? So we're going to test out case 2 first. So we're going to say n to the power 1/2 is equal to theta of n to the power c, where c is also 1/2. And actually, in this case, yeah, that works perfectly, because c is 1/2, so is f of n. So we found our match. So definitely case 2 is definitely the best one to start with. So for this situation, since case 2 matches, therefore t of n is going to have to equal, so looking at the master theorem notes, going to have to equal theta, so I'll put this over here. We found a case 2 match. So we're going to say theta is going to be n to the power c, so I'm going to put root n log n is the result of this one. Let me see if my notes matches. Yes, n to the power c, so c is 1/2. N to the power 1/2 is root n times it by log n. So I think in my notes I made a mistake actually. I put theta of root n on my notes, but it's definitely root n log n, because that's what case 2 actually does. Let me just double check this. So it's n to the power c log n. So that is the answer there. So I'll have to update my notes, my notebook on this then. So that would be this question 15. That's the result. So root n log n using the master theorem. So I got a few more to do here. So let's do 16, another simple one. The last two will be sort of more trickier sort of methods of the master theorem, where it appears to be that it can be done using master theorem, but then there's going to be a little bit of a contradiction. But let's first do this last sort of simple-ish one. So t of n equals 2t n over 7 plus theta n squared. And then t of 1 will, of course, equal 1. That's our base case for this recurrence relation. So once again, we'll get our constants. So a equals 2, b equals 7. Therefore, c will be log base 7 of 2, which will roughly be 0.3562. It was a log b of a for the master theorem to get our c value. And of course, f of n is just going to be n to the power 2, which right there, theta n squared is our f of n. Okay, so once again, let's start from case 2. So let me go to my notes and just make sure I kind of have everything in front of me here. So case 2 asks if f of n equals theta of n to the power c. Well, n to the power c would be n up to 0.3562, so case 2 can't happen because n squared is not going to equal theta of n to the power c in this case. So case 2 is already eliminated, basically, so we can't have a case 2. Okay, fine. Let's look at case 1. So for case 1, f of n equals O of n to the power c minus epsilon. Well, let me just go ahead and outline case 1 over here. So case 1 is asking if n squared equals O of n to the power c minus epsilon. Well, n to the power c is already less than 2, so this cannot bound n squared, because if I subtract it by some epsilon, it's going to, well, it already, so let's say if epsilon was 0 even, this would still not work, actually. So this is definitely not going to work. So case 1 is also not going to be used. So probably case 3 has to work. Let's go ahead and just test this out for case 3. So case 3 is asking for if n squared equals omega n to the power c plus epsilon. So I'll pick epsilon just to be, I don't know, 0.1. Then this will be omega of n to the power 0.4562. So n squared is equal to omega of n to the power 0.4562. So case 3 happens in this situation. So just pick some constant, any constant. If it can work for epsilon, just for any constant, that means we identified the case for the master theorem. So case 3 happens in this scenario. So the case 3's results, well, let's see, once we identify the case, let's see. So for case 3, so if, let me see, I guess it also asks this part as well, which is, I don't understand the real purpose behind this one, but you also have to make sure this is also correct, where a of f of n, which is going to be n squared, so a, which is going to be, I guess, in this case, 2. So 2n squared over 7 has to be less than or equal to some constant z multiplied by n squared, where z has to be less than 1. Well, I guess if z is 2 over 7 or smaller, then this actually works. So case 3 actually happens. I don't really see how, I guess there are certain cases where this could mess up, but I guess here, well, we identified the case 3, and this also has to be correct as well, because z can be 2 over 7, which is less than 1. So this is true, and this is also true. Therefore, case 3 is going to happen. So then the result is going to be theta of f of n. So f of n in this case is n squared. So theta of f of n, or theta of n squared, is the result of this. So those are kind of our several examples of master theorems. So I kind of showed an example of where case 1 happens, case 2 happens, and where case 3 happens. So that's pretty much, for the most part, that's going to be kind of how you solve these master theorem type of problems. Oh, okay, so I made a mistake there. So actually, it would be plug in n over b, and so it would be that thing, because a goes on the outside of f of n. So yes. So either way, however, we still works out. So yes, my mistake right there. So you plug n over 7 in for a, or for n. So there we go. So that would be the results there. But still, we can pick z just to be 2 over 7 squared, which works out. So thanks for the correction there. But either way, though, it will still work out. So we get O of n squared, with theta n squared as our result. So that's that. So let's see, what else do we have here? So I think I have, let me see, this one is 16. So let's see, so we have another, so I guess I'll do one more case, and then we'll get into the last 2 cases where it gets a little bit more trickier. So let's do this last one, this last sort of simple one before we have our other 2 weird ones. So So I have theta of, this one's actually a weird one as well, actually. These last few will be kind of strange. So let's see if we can sort of work this out, or let's see if I can actually not mess this up. So we'll have t of 1 equals simply 1. So we'll have a as 3 again, b as 4. F of n will just be basically n times log a of n. So I'll actually not really a, but I'll just maybe use different constant here, log r of n. So just any base I really want to use for this log function. So anyway, we have that. Then c is going to be log 4 of 3, which will be essentially 0.79248. So let's go ahead and once again try to work out the master theorem on this one. I'll go back to my master theorem notes since I can't memorize this master theorem. Actually, maybe I could start to want to do enough of these, but why? Let's try to be careful and get this correct. So let's first start with case 2, as always. So for case 2, f of n equals theta of n to the power c, and it's not correct. We already can see it because n to the power c is n up to 0.79, f of n is n log n, so case 2 does not work. We already can see that. So let's try case 1. So case 1 and 3 are the more trickier ones, I suppose. So let's try to test out case 1. So for case 1, f of n, which will be n log base r, so we don't really know what the base is. It doesn't really matter what the base really is, but I'll just keep that kind of anonymous for right now, equals O of n to the power c minus epsilon. So I can pick a big enough epsilon where, actually, no I can't, because this already won't work, because, I mean, we could do L'Hopital's rule and so forth. We also can just visualize this, that n, since n times log n, this left side equation grows at a faster rate than n. This one's below, so n to the power less than 1. So this definitely cannot work already. So if it's subtracted by epsilon, it will be even more obvious that this will not work, because this n to the power of something less than 1 is not going to grow at a faster equal rate than n times anything. So we already know case 1 can't happen. So that leaves us with hopefully case 3 will work in this scenario. So for case 3, we'll have n log r of n equals omega n to the power c, c plus epsilon. So epsilon, once again, I'll just pick the same one. Why complicate this? 0.1. So we can see it'll be n up to the power 8, n up to the power 0.89248, which is going to work in this case, because since this function inside of omega is actually a lower rate than n, it definitely it's going to be correct to say that this function n log r of n will grow at the equal or faster rate than n to the power with some exponent less than 1. So case 3 so far works. We have to also test out this last part. So we'll also have a, which will be, I guess, what's a? A is going to be 3 times it by n log r of n over, so this will be b squared. I think it's going to be actually over b, never mind, because we're not. Actually, it's going to be n over 4. Like that. That's my mistake. So let me just fix this. So we substitute n over 4 in. Like that. Less than equal to z times it by n log r of n. And I won't really go over all of this, but you can kind of show that this is going to sort of work. So let's say I guess as long as, let me see. So n log r, and this is going to be larger than this part, so long as, so this actually will work as well for zeta. So this will also be correct. So at least I have to check that's like work this whole thing out. But anyway, this will actually also be valid. So then this will give us the result of theta f of n, which will just be n log n. All right. So, I mean, I actually looked this up recently, but I never really was exposed to master theorem where you had to work out this part. So typically, I would just say you have to only figure out if this works. And that's how I was most exposed to master theorem. So in the book, I looked up this second part over there, which I'm still a little bit kind of fuzzy on that. But for the most part, if you can match this, then you're actually okay. Then you have your results. So I have to like maybe spend a little more time looking at what this portion is really trying to imply. But from what I was sort of taught the master theorem, basically just if you can match this portion right there, then you're basically you have the case three scenario. So actually, I worked these out where I didn't actually even do this and part there. But anyway, yeah. So first check is actually good enough. I was never really exposed to this one when I was back when I was undergrad. I learned algorithms. I never actually really looked at this. That first check, if you do that, then you're fine. So that's what I actually did on these. So that's why I kind of got a little messed up. I'm doing this on the fly. This second part right there, whereas I just worked this out using that first check. So I would just say stick with that, and then you're fine. Okay. So I guess here's the last weird one. So that first one, this question right here, using a log function, we were able to match it to case three because we know that n times log n will grow at n level or higher. In this sort of omega function, we have c, which is less than 1. So we can kind of, sort of show this is going to work because n times some function will be definitely larger than n, and this omega part is less than 1 for the exponent for n. So it definitely works. But then let's go ahead and have this last portion right here. Question number, so last sort of recurrence relation, number 18. This will be definitely the weirder one. So let's go ahead and start talking about this. Like that. Of course, t of 1 equals 1. Okay, so in this case, it looks like it would be able to work with one of our cases, but let's go ahead and try to see how this does not actually work with any of our cases. So this one's not going to work, but sort of see why it is not going to work. So A is 2, B is also 2, therefore C will be log 2 of 2, which is going to be 1, and f of n is going to just be n, and I'll just pick a difference, log r, I suppose, of n, doesn't even matter what the base is, so I'll just pick just any log base. So as always, let's start from case 2 as our starting point. So let me go back to my master theorem notes so I don't mess this up. Okay, so case 2, we have basically f of n equal theta n to the power c. So n to the power 1. So n log n equals theta of n. Well, that's not true. So case 2 is already gone. So let's look at case 1 now. So case 1, let's test this one out. So we're going to have f of n, which would be log n log r of n equals O of n to the power, I'll just use 1 for right now because c is 1 in this case, 1 minus epsilon. Well, in fact, even if it was just 1, it wouldn't work. But if I pick some epsilon of any value of any type, so I'll write just a little nicer as epsilon right there, it's not going to work. So we can't really bound it using case 1 because obviously n times log r of n is going to have at least an n sort of growth rate. So there's no way we can actually make this work. So case 1, there's no epsilon that can work, and this is not going to be correct. So case 1 fails. How about case 3? So n log r of n equals omega of n to the power 1 plus epsilon. So here's where it's a little bit interesting. So basically, let's go ahead and just try to use a little math to try to work this one out. So I'm going to substitute 1 plus epsilon to be, let me pick, I'm going to choose this will be t, I suppose. Okay, so we're going to have n, actually I'll just keep it like this. So n log r of n equals basically n to the power 1 multiplied by n to the power epsilon. Where epsilon is some value larger than, actually it's supposed to be like this, some value larger than 0. So we can eliminate these parts right there, and we're left with this. Where epsilon is going to be larger than 0. So I believe the other day I showed this using L'Hopital's rule that if n to the power of some value up to a base that's larger than 0, the log of r is going to actually grow at a slower rate. So I believe I went over that last time. So I went over it for a reason, actually. So that means that log r of n is not asymptotically bigger than any sort of polynomial function. As long as n to the power of the exponent is larger than 0, then log r is going to actually have a slower growth rate. So this is actually not true. Using L'Hopital's rule, we can prove that that's not correct. So case 3 also fails. So case 1, case 2, and case 3 all fail. This one you cannot really use master theorem to solve. So now for exam questions, at least for the homework, you can solve using master's theorem. I'll try to not have too many of these on the exam to throw us off too much. But this is one case where the master theorem isn't going to work. So typically for these log functions where it kind of messes up. And also at the same time, there's certain sort of expressions where it won't even, you can't apply master theorem at all. So for example, like t of n equals t of n minus 1 plus 1, you can't really apply, at least you can't apply this master theorem on that expression. So yeah, so that was several examples of the master theorem for several problems. So really, overall, it wasn't really too hard to work these out. So I'll look into what that and part for case 3 is supposed to mean, but I never really was exposed to that when I was younger. So there might be a specific reason for that. But for case 3, if you just match it with that one, with that first condition, it should be fine. But I'll maybe look into that a little bit to see what's the deal with that. But for right now, the master theorem is just sort of a nice sort of plug and play sort of way to work out recurrences without having to do the whole expansion. Now, when we do different algorithms in this class and I have a recurrence relation presented, I'll use master theorem to solve it because, why reinvent the wheel? Except, on homework and on exams, you're going to have to expand it out because just as a fun exercise to do that. But of course, in class, we'll just, from now on, we'll use master theorem to solve these because, just to make the whole process kind of easier. So anyway, now we can officially sort of actually talk about actual algorithms, which is kind of nice because we are in the second week of this class, so it wouldn't hurt to finally discuss all of that. So let's go ahead and begin with actual sort of algorithms. Homework 1 solutions right there. I probably shouldn't click on that because I think that would kind of ruin the whole fun of working on homework assignment 1. So I think I'll try to not show that by accident here at all. So let's go over sort of divide and conquer. This will be for multiplication. I spelled conquer probably wrong. How do I spell conquer? I spell like that. Okay, great. I spelled conquer correctly now. So divide and conquer. So this is going to be like the first sort of set of algorithms we'll study in this class. So I guess for one, what is divide and conquer? Well, divide and conquer is we sort of break the problem. So given some problem that we're trying to solve, we break the problem into smaller parts. We can call these as subproblems. And once each subproblem has been computed, we sort of combine each subproblem to solve the original problem. So that's kind of my, off the top of my head, definition of divide and conquer. But that's really all there is to it. So the thing is, when we do something divide and conquer, because we break into smaller pieces, we actually can find ways to sort of enhance the runtime by doing that. And we saw this in 302, where when we did sort of sorting, we did merge sort and quick sort, and we actually got a better runtime because of divide and conquer over bubble sort, session sort, and insertion sort, at least in the worst case for insertion sort, and also the average case as well. So we're trying to take this problem, break it into smaller pieces, and we're going to attack we're going to attack the smaller pieces the same way as the big problem. So we just sort of create these sort of recursive function calls to solve each small piece like that. So it's kind of like where, I guess, like in Germany, when we sort of build cars, they could have one sort of car plant where they sort of all the cars together in one plant. But what they do for like BMW and Audi is that in different countries in Europe, so in one country they have them design or build the engine, other country they have them build the transmission and so forth, and they have all that created in several different spots, and at the end they assemble it in one place together in some location in Germany, I'm guessing. So that actually does give us a nicer, you can do more production that way, because you can have more production of cars in that kind of way. Also for like big data and for like Hadoop, which I'm not an expert on this, but I know in big data you get the data, there's sort of all kinds of servers everywhere, and then when you want to do retrieval, each server sends the data out, and then you have to kind of use that sort of map reduce to put them back together. And that way you can sort of retrieve a lot of data much faster than having it all on just one server like that. So breaking out the problem into pieces and putting it together does seem to have a sort of favorable sort of output, favorable result. So we're going to be doing this for for this class for algorithms. So we're going to first start off by talking about multiplying big numbers to each other. So let's go over multiplication. So long multiplication. Sort of that grade school multiplication. So I'll go ahead and sort of talk about this. I'm not going to actually work this up kind of from the bottom up, because I think we know how this works, but let's go ahead and just go over this. So I'm going to have a number A and a number B. And let's say A has a set of digits. So we have A1, A2, A3, and up to A sub n. And B has a set of digits, B1, B2, B3, up to Bn. So we can suppose we can actually have these two numbers stored into a vector of integers, where every single index of this vector would be just sort of the actual number stored in that index will be sort of the coefficient, and index will be a place value of where that coefficient resides. So in my 202 class way back in the day, I would actually have my students work out a library for big number and have to actually manually do all this. So definitely seemed like the grade school multiplication became a challenge in CS 202, which was kind of funny, but it is. I mean, if you work it on paper, it's fine, but coding it though, I guess apparently you have to be careful with all this. But anyway, to work this out, well, how do we actually do this? Well, the first step is we take the rightmost digit of b of n and multiply that to everything in A. So we're going to get b n a n, then we have b n minus 1 a of n, b n minus 2 a of n, until eventually b1 a n, right? So we basically just take this left to rightmost digit, multiply it to this digit, that one, to each one by one, right? And we get this sort of partial result. And then for the next sort of step, we put a 0 over here. And now we have b n minus 1, a n minus 1. Then b n minus, actually, oops, it's supposed to be a minus 1, a minus 2. It's supposed to be eventually b n a1, my mistake. There, so that's how it's supposed to be. So we'll apply b to each digit of a. So if b n minus 1, a n minus 1, then b n minus 1, a n minus 2. Then we end up getting b n minus 1, a1 at the very end like that. Yes. And then, of course, let's do one more step over here. So we add an extra 0 over here. Then we have b n minus 2 multiplies to a of n. Why am I making this mistake here like crazy? So I have n minus 1. Okay, so then we do all of this to get b n minus 2 a1. So the standard, multiplication of these numbers. So apparently I have to relearn my second grade multiplications, but that's sort of how we do it. So bn multiplies to every digit of a, then bn minus 1 multiplies every digit of a, and so on and so forth. So I guess my notes were correct, but I sort of try to do this without that. But anyway, that's sort of the method, and we have to, at the end, add all of these up. So basically, to construct all of these, so essentially, to construct all of these partial sums, so the runtime to construct the partial results, well, if both numbers are n digits, then it will take you theta n squared to compute all of these results, because b of n multiplies to every digit of a of n, that takes n time, then b of n minus 1 to all of these takes n time as well, and so on and so forth. So it'll be theta n squared time to construct these. Then the question also is, okay, so now we have that. So it took theta n squared to first, create these partial sums. And then how many partial sums are we going to actually have? Well, there's going to be n of these. Because for each digit, b of n, so b of n minus 1, b of n minus 2 up to b of 1, each of these will create one sort of partial sum. So we're going to have actually n of those. So, okay, that's great. So what's going to be the runtime to add all these up? Well, also, before I even do that, the number with the biggest number of digits, so the max number of columns, or the max number of digits we're going to have here is going to be 2n. So a max number of digits will be 2 times n. Because remember, we're multiplying two numbers of size n, so the number will end up being 2n. That's just, another sort of second grade or grade school sort of multiplication kind of, that's sort of the, I guess, the rule there. So we're going to have to do this sort of summation 2n times, it's going to be 2n number of total columns. So to add these up, well, for the rightmost column, we're going to have bn a of n, and we're going to add it to a bunch of zeros. So really, it requires no additions at all, to be honest, because adding by 0 is really nothing. Next column, we're going to do 2 additions. The rest will all be zeros. after that, because to fill this sort of thing out, eventually we're going to get b of 1, a of 1 like that. If we keep doing this, we're going to do more of these. So essentially, everything below will all be zeros. So in this rightmost column, we do 0 additions. This next column will do 1 addition. The rest are going to be all zeros if we do our second grade multiplication correctly. So there's no more additions to be done. The column after that, we're going to do 3 additions. The rest will all be zeros, so no additions are needed. So there's a very nice pattern for how this is going to actually work, the runtime to add up all these partial sums. So the runtime to add partial sums is going to be, well, the summation from I equals 0 to n I. And it's that formula that maybe learned from 302, maybe you did not, but it's Gauss's formula basically. So we're doing 0 plus 1 plus 2 plus 3 up to 2n, and this amount is going to be theta of n squared. We actually can work out the math because there's a very nice formula that does this, but I'm not going to really go through all of that, but this summation will give us theta of n squared. So that means we first have to construct these partial results. So that multiplication part, we have to match, b of n to a of n, b of n to a of n minus 1, and so forth. All that takes n squared time, plus the runtime it takes to add up all the sums. Well, we get a total of theta n squared runtime to do this. So basically, the total runtime is going to really be the time to construct the partial sums, which will be theta of n squared, plus time to add partial sums also takes theta of n squared. So the grand total will be theta of n squared. So that was our standard grade school multiplication algorithm that you learned. So you've already been exposed to algorithms way back when you were in grade school, and this algorithm was theta of n squared. So, of course, if you have a 9-year-old, child, you tell them like, yeah, this is theta of n squared runtime, and then the kid will give you this look of, what are you talking about? And, but I guess, you'll find out later, maybe, I don't know. So that's the runtime for this. So up to this point, so after a certain point, it was sort of, almost like proven, or kind of not really proven, but it was sort of stated. So it was stated, I believe, that multiplying two numbers of size n is omega n squared, which means a lower bound. So this implies that you cannot do less than n squared number of steps to do this. That was kind of what was stated, at least back in the day, whenever that was. So if you found something that was better than n squared, well then no, that can't be, because we set the bar at n squared. You cannot construct anything better than that. So lower bounds are mostly used to design that you cannot do better. So no algorithm can exist that can be better than n squared. But let's first go over maybe trying to use divide and conquer to work out this sort of, how shall we say, multiplication problem, and see maybe we can prove this statement wrong, that we can find something that will work and it'll be better than omega n squared. Actually, in fact, I wouldn't be talking about this right now in so much detail if we couldn't do better than omega n squared. So I guess the answer already is, we can find better than n squared using divide and conquer. This will be kind of like a Zack Snyder sort of way of doing this. You first start off with, yes, this can be done, and then we go back into the story and go over how it led to that part. I guess that's how it always works. You know, at least not always, but that's some of Zack Snyder's sort of, at least his movies are very not linear typically. So I guess this is a non-linear um, sort of lecture. We start from the very end and work our way forward. So, okay. So let's suppose for right now we have the following examples. Let's try a divide and conquer approach to this. I'm going to try to spell conquer correctly. I might have taken too many French classes when I was younger, so the E and the U at the end kind of seems to make sense to me, but in English, though, it's not like that. So I guess that's probably my mistake. I shouldn't have studied French in high school. So, okay. So suppose we multiply two numbers. So again, we're going to multiply A times B, where A and B are both going to be n-digit numbers. So where A and B are n-digit numbers. So let's go ahead and try to think of it like this. So I'm going to show you this method, and of course, then we can go ahead and sort of, I'll try to explain this further. So let's try the following method. So we're going to have A11 times 10 to the power n over 2 plus A12. Multiply that by B11 times 10 to the power n over 2 plus B12. So basically, in this definition, A11 is going to be the leading. So basically, we're going to take this number A and break it into two halves. So we'll assume for right now, for this for this analysis, that n will be a power of 2. So we break the number into two pieces. This is the first half of A. This will be the second half of A. This will be the first half of B. This will be the second half of B. So let's go ahead and do an example just to talk about this, and I'm going to erase it and then just go on with my notes. But first, just talk about this. So assume that, let's say, we have the following scenario. We have something like, it's randomly going to pick a number. So 1, 2, 3, 4, multiply it by 5, 6, 7, 8. So we're going to go ahead and do the following. So 12, multiply it by 10 to the second power plus 34. Multiply this by 56 times 10 to the second power plus 78. So we just sort of broke apart the number in two pieces. So this is going to still be the same correct, multiplication. This is still valid. We just simply broke apart this number because this sum in this parentheses is going to be 1,234, and this sum will be still 5,678. It's almost like, think of the following. If I do something like 5 times 7, I can make this into actually 3 plus 2 multiplied by 4 plus 3. That's still valid to say that, right? So that's what we're essentially doing over here, because this is a bit more extra work in a sense, but this is mathematically still sound to the same problem. So we're trying to break the problem into two pieces for right now, because we want to be able to divide this work up into smaller problems and then at the end combine them together. And multiplying by 10 to the power n is simply a bit shift. We just add zeros to the end of the number. So there's no real multiplication to be done there. We just sort of add zeros to numbers. So that operation is actually quite linear. So that's what we mean by we're doing this. You take the number and you break it into two pieces. So in this case, 12 would be A11. 3, 4 would be A12, and 5, 6 would be B11, and 7, 8 would be B12. That's all this really is. So I'm going to go ahead and erase this, but that's what I mean by that. So we're trying to break this number into two pieces, into half like this, so that way we can actually create our subproblems to basically do this in divide and conquer type fashion. So now let's go ahead and just go over that. So in this case, if you were to distribute out this multiplication, we get the following result. I'm going to go ahead and just use my notes here so I don't mess up this example. So we end up getting 10 to the power n, multiply it by A11, multiply it by B11, plus 10 to the power n over 2, multiply it by A11 times B12, plus A12 multiplied by B11, then at the end, plus A12 times B12. So I believe that is the correct distribution of all these, because we're going to first have so we distribute this correctly, we have this term multiplies to this term to give us A11 times, I'm going to zoom out so you can kind of see all of this. So let's see if my notes are correct. But this will give us A1 times B11, and they're both n over 2 size digits, so the result will be an n size digit. And then after that, multiply this with this, which will essentially be A11 multiplied by B12, and it'll be an n over 2 size digit. Then multiply this with this to give us A12, B11, which will also be n over 2 size digits, so we can put under one umbrella. And then we have A12 multiplied by B12. So it looks like what I have right there is correct. So we simply just distribute this out and we get this result over here. So this is going to give us the result they're looking for. So the thing here is every multiplication, so not this 10 to the power n part, because this is really just simply a bit shift, or we're just adding zeros to the end of the numbers. So really, the multiplications that we have here are really, these are the multiplications we have to worry about. And the 10 up to the n, or 10 up to n over 2 part, we can just sort of at the end just sort of put those in. So essentially, each multiplication will be done recursively. So each multiplication is its own subproblem. So each is its own subproblem. And of course, after the magic of recursion, which, recursion is all magic, it just sort of, recursively call a function and it returns back a result. So once we get each result back, then we just go ahead and combine them all together. It's kind of like we have the transmission will be done in Hungary. We'll have the engine done in Austria. Then we'll make some other parts. We'll do this in Slovakia. And I think the last one I'll say is done in Germany. And at the end, we're going to assemble all the parts in Germany, is what we're going to do here. So each part will recursively do its own thing independently, returns back the results, then we just combine them all together. And then once we have each result done, so I'm going to put this over here. So once each subproblem is computed, we just add them all together. We first we add, either n or n over 2 zeros to the end of some of the subproblems, not all of them. and add them all up. So this complete addition of adding up all these subproblems together, so time needed, so time, sort of the time complexity of this is theta of n. We took the problem that was an n-sized number, broke it apart into pieces, and we just magically computed each individual subproblem. We get those subproblems, we just add them all together, and it takes n time. So adding extra digits on there takes n time, and then adding all those numbers up is a linear operation. Adding up two numbers of size m is a linear operation. So this will take theta of n time to add these all up. So what we're going to do is recursively keep on calling this function until multiplying two numbers that are size 1, because size 1 will be our base case. It takes sort of one operation to multiply two one-digit numbers. So we break this down further and further. So we have to recursively process this part, then this part, and this part, and this part, and put them all together. So let's do an example. Let's begin an example on this, and then we'll go over the runtime of this and see if maybe we can also do other things to this. So let's do an example on this. So I'm going to just sort of, I'll make this a little larger. Yeah. So let's do an example. To get an idea of how this actually works, we actually can really understand sort of the nature of how divide and conquer can be used to solve a problem. So we're going to have A. We're going to have A is going to be 3, 7, 2, 4. And B will be 9, 8, 9 studios, or 9, 8, 9, 5, I'll just say. So these two numbers. We will multiply them together. So I actually already multiply them using the grade school method or using a calculator. Let's first put the answer right here so we can kind of just, see if we get to the result using divide and conquer. So the result will be 36, 4, 8, 4, 8, 9, 8, 0. So that's the result. So I put that there just so we can see if this result, if we do end up getting the same result using divide and conquer method. So the math is pretty sound there, but of course you want to work this out sort of manually. So work out using this divide and conquer part manually. So we first work this out. Well, we're going to break this problem down into pieces. So in this case right here, initially, so I'll sort of copy this down over here. So let's go over, now we'll do the official divide and conquer part. So A is going to be 3724. B is going to be 989 studios 995. So basically, this is going to be A11. And this will be, I guess, A12. This is going to be, I guess, B11 and B12. So if we apply our formula, well, we're going to have 10 to the power 4, because in this case, n will be 4 in this situation. We have a 4-digit number. We're going to take 37, multiply it by 98, plus 10 to the power 2, because n is 4 in this case, n over 2 will be 2. Multiply it by 37, multiply it by 95, plus 24, multiply it by 98, and then plus at the end, 24, multiply it by 95. So each multiplication is we're going to call the function recursively, but we're going to pass in a smaller number each time. So initially we call this in main, let's say, we passed in A and B, and within this function body, we're going to make a function call and pass this in. So in this situation, 37 will be A for this new function call, and 98 will be B for that function call. Let's first process this part. So we're going to have, in this case, A will be 37, and b will be 98 for this instance. Remember, we recursively call functions, so we're kind of pausing right here. We have to process this part in recursive fashion. So in this situation, well, A11 will be just simply 3, A12 will be 7, B11 will be 9, and B12 will be 8. So you have these one-digit numbers like this. So what we're going to do now is, again, we're going to do the same exact problem, but for this smaller instance. That's how recursion is done, I believe. So we're going to now have this situation. So we're going to have, I'll just list this out here. So A11 will be 3, A12 will be simply 7, B11 will be 9, and B12 will be 8. So if we apply that same formula on this instance, we're going to end up getting basically 10 squared multiplied by 3 times 9 plus 10 to the first power multiplied by 3 times 8 plus 7 times 9 plus 7 times 8. So in this case, well, we would actually call the function again, but I'm not going to go through this whole function call again because it's going to take too long. It'll take too long to work this example out. But what's going to happen is we're going to just multiply 3 times 9 because, well, they're one-digit numbers now. So actually, in this case, this would be our A, that would be our B for another function call. But we'll just sort of do this right here at this level instead of calling another function to like make this problem not so large. So we'll just go ahead and call a function recursively and get the result back, which will in fact be just 10 squared multiplied by 27 plus 10 to the first power multiplied by 87. So we just work that part out there, and then plus 56. So this will give us a total of 3,626 is the result of this function. So return back the value. In this case, I'm just going to put this here in red. So 3,626 was computed by the recursive function. Awesome. So now we have to go ahead and do this part. So I'll do this last example, this last one, and we'll stop and we'll continue this next week. But just do this one last part. So you have to now call the function where this will be A, 37, and B will be 95. So we're passing in these two numbers into a different recursive function, just like how we do recursion from 202 or 302. We just pass in these two numbers in. And it's going to be a different, smaller instance of this problem. So we have a subproblem right there. Let's go ahead and now work this one out. So you have a new function call. In this function call, A is going to be 37, and B is going to be 95. Let me make sure I correctly identify them. Yes. So in this case, A11 would be 3. Oops, A12 would be 7. B11 would be 9. And B12 equals 5. So we do the same exact problem. We just sort of put this together just like we did in the earlier example. So we're going to say 10 squared will simply be 3 times 9 because we have A11 times B11. And then plus 10 to the first power, multiply by 3 times 5 plus 7 times 9. And then at the end, plus 7 times 5. So again, we have 10 squared multiplied by 27 plus 10 to the first power multiplied by, I guess 78 is the result of this. I worked this out earlier. And then plus 35. So if we add all these up, we end up getting 3,515 is the result of that. So we're going to simply copy this. We're going to pass this result back up to the recursive function. So the previous function, I called it right here, we return that result back right over here, which will give us the result of, I'll remove this, 3,515 is the result. So if we continue this process, we next have to compute this part. Then we have to do this part. So I guess I'll do those last two steps next time. We add this whole thing up. This should give us this result. So I already worked this out and sort of tested it and made sure I didn't make any mistakes. So this does end up giving us that result. So once we do that, we got a result. Then we'll do some analysis on the runtime of this algorithm and recap a little bit of this next time. And then we'll see if maybe with this sort of divide and conquer approach, maybe we can try to modify it a bit to hopefully get maybe even a better runtime than what this particular example would give us. So I guess for right now, that'll be it. So I will continue on this next time. So homework is due tomorrow. Assignment 2 is already up. So I guess take care, guys. Thanks for watching. Have an awesome, nice long weekend. We have Labor Day weekend coming up. And I will see you guys next week.